So in this video, I'm going to run through electrolysis. We'll start with the absolute basics. So the word electrolysis literally means the use of electricity to split something up. And in terms of what we'll be splitting, we'll either be looking at an ionic compound or we'll be looking at water. So if I have an ionic compound, something like aluminium oxide, it's ionic because it's got a metal and a non-metal. I use electrolysis and I split it up into the metal, aluminium, and the non-metal oxygen. Okay, the reason I would do this, aluminium, pure aluminium, can be used to make cars and it can be used to make planes. And although aluminium is really abundant because it's reactive, when we find aluminium, we don't find it in the pure form, we find it as aluminium oxide. It's already reacted with oxygen. To get aluminium in its pure form, we use electrolysis. We separate the aluminium and the oxygen, and then the aluminium can be used for cars and for planes. We can also split up water. Okay, water is obviously made of hydrogen and oxygen. We can split up water so that we get the hydrogen and the oxygen. Hydrogen can be used as a fuel. We saw that in CC16, and even though there are other sources of hydrogen, so natural gas would be a source of hydrogen, it's not a renewable source of hydrogen, so being able to split water up and get hydrogen is useful. Downside of electrolysis though, because it requires electricity, it is expensive to do on large scale. The fact that it requires electricity is the focus of the next little section here. If your compound doesn't conduct electricity, electrolysis will not work. So I said we're going to split up an ionic compound or water. In the case of the ionic compound, to make it conduct electricity, I can either melt it or I can dissolve it. If I melt it, I give it the state symbol L, and I can also describe it as molten or liquid. If I dissolve it, I give it the state symbol AQ, and I call it aqueous, or say it's in solution. So once my ionic compound is molten or aqueous, it is able to conduct electricity. Why? Because now the ions are mobile. They're free to move and they can carry current. You should not be talking about delocalized electrons when you're talking about ionic compounds. With water, water is a covalent molecule, but to make it conduct electricity, if you add some acid, the acid will provide the H+ ions needed to carry the current. So ionic compound, you're melting it or dissolving it to get it to conduct. Water, you're adding a bit of acid to get it to conduct, and once it can conduct, you can use electricity to split it up into its elements. A little bit of terminology here, all right, so this is your typical setup for electrolysis. We're using electricity. That electricity is supplied by a battery, and then down here in this beaker we've got the electrolyte, which is the substance you are trying to split. So let's say, for example, this is an ionic compound, maybe it's sodium chloride. In order to get it to conduct electricity, I would have dissolved that sodium chloride in water or melted the sodium chloride, and that's why my electrolyte is shown in liquid form. In order to get the electricity from the battery into my electrolyte, which is the thing I'm trying to split up, I'm going to use electrodes. I connect the positive end of the battery to one electrode, the negative end of the battery to the other electrode. You can use a variety of things for electrodes, but they need to meet the following criteria. They need to be inert. That means unreactive. You don't want the electrode to react with the ions in your electrolyte. It needs to be able to conduct electricity. Hopefully that's self-explanatory. I need the electricity to pass from the battery through the electrode and into the electrolyte. I want them to have high melting points. You're going to need to use high temperatures if you have melted your ionic compound to stop that ionic compound becoming solid again. And you don't want your electrode to melt into the ionic compound. So I'm going to have high melting points. Typically we use graphite, which can conduct electricity and has a very high melting point, or we use platinum, which is a metal. Next part is the electrolysis process itself, and this is where things tend to get maybe a little bit trickier. There are two steps to this process. Step one is the easier bit, all right? So I need to split the compounds into ions. So the electrolyte is whatever it is we're splitting, or maybe our ionic compound, and it's made up of ions. And what's going to happen, if I come down here to an example, all right? So this would be an example of an electrolyte, sodium chloride. And sodium chloride is made of two ions. It's made of a positive sodium ion, and it's made of a negative chloride ion. And what will happen is when you turn on your battery and your electrode becomes positively charged and the other one becomes negatively charged, your ions are going to be attracted to the oppositely charged electrode. So all of the sodium ions, which are positive, are going to be attracted to that negative cathode, and all of the chloride ions, which are negative, are going to go to my positive anode. So if I were to fill that in over here on my original diagram, all right, this one here is positive. This is where my Cl- ions are going to go. This one here is connected to the negative side of the battery. This is where my sodium ions, which are positive, are going to go. And the negative side is called the cathode. You'll need to learn that. And the positive side, the positive electrode, is called the anode. So I can split sodium chloride into positive and negative ions. The same thing will happen here. I've got another ionic compound, magnesium bromide. Magnesium bromide contains 2 ions. It contains Mg2+ ions, which will go to the negative cathode, and it will contain Br- ions. Again, the minus ions go to the positive anode. So what I can see here, if I just look, my ionic compound, you always have the metal first. So sodium is my metal, magnesium is my metal, and in both cases, my positive metal ion is going to my cathode. My negative non-metal ion is going to the anode. And that's a rule, right? The thing that comes first will be positive and it will go to the cathode. The thing that comes second will be negative in an ionic compound and it will go to the positive anode. My final example is water. I said you can use water. You need to make it conduct electricity first, so you chuck in some acid, usually sulfuric acid, and then you can split up the water. And water can be split into H+ and OH- ions. The H+ ions go to the cathode, opposites attract. The OH- ions go to the anode. But that's only step 1, all right? Separating the compound into ions is step 1. Step 2, the important part, you need to turn the ions back into atoms. You need to get back to the elemental form, all right? And at the moment, as ions, they're not in the elemental form. So let's come down here and have a look at what's happening at the cathode. So I'm sticking with NaCl. I've just separated the ions. So I've got the Cl ions and Cl- ions at the anode, and I've got the Na+ ions over here at the cathode. At the moment, sodium has a positive charge. It is an ion. I need to get rid of that positive charge if I'm going to make it an atom again. If we think about what the positive charge means, the positive charge means that sodium had lost an electron. If I give it that electron back, it won't have a charge anymore and it will be back in its elemental form, which is what I want. If I look at my magnesium example, it's the same thing. Magnesium has a 2+ charge because it has lost 2 electrons. If I give it those 2 electrons back, it won't be charged, and that's what I'm trying to do. I'm trying to remove the charge from my ions so that they are no longer ions, they are now atoms again. The hydrogen example, slightly trickier, okay? Again, I've got my positive hydrogen ions, okay? And if I were to write this out initially, I would have H+, and I want to turn it back into H. I don't want it to be positive anymore, okay? So to do that, just like I would have done above, it's positive because it lost an electron. I'm going to give it an electron back, and I'm turning a hydrogen ion into a hydrogen atom. But then I need to remember that hydrogen, when it's an element, does not exist as H. It exists as H2. It is diatomic. And if I've got 2 hydrogens on the right hand side, because it's diatomic, I need to balance this using a big number to show I've got 2 hydrogens on the left hand side. And if I've got 2 hydrogens, each of them need to gain an electron, so I need 2 electrons in total. So this big 2 here means I've got 2 separate hydrogen ions. Each of them gain 1 electron, and when they are both hydrogen atoms, they can combine and form H2 molecule, which is how hydrogen exists as an element. So that little 2 is telling you that 2 hydrogen atoms are bonded together. That big 2 at the front is telling you the 2 hydrogen ions are separate from each other. They cannot form a bond because they're both positive and will repel each other. So what I'm showing here is that after I've separated the ions into negative and positive, I need to turn them back into atoms. And for my positively charged ions, that means gaining electrons. And we call this process reduction. So if you're gaining electrons, you're being reduced. And that's what's happening here at the cathode. At the anode is going to be the opposite, all right? So I've got all of my negative ions going to my positive anode. Now, if I look at chlorine, again, I'm going to start off by writing it alone down here. My chlorine is negatively charged because it gained an electron. If I take that electron away again, it's going to be back to just being a chlorine atom. But just like hydrogen, chlorine, and indeed all of your group 7s, are diatomic. So in its elemental form, it doesn't exist as a chlorine atom. It exists as a chlorine molecule. There are always 2 of them. They're always in pairs. And to balance this, again, I'm going to need to put a big 2 over here. 2 totally separate chloride ions. Each lose 1 electron. So 2 electrons lost in total. Once they've lost their electrons, they can pair up and they can form Cl2. And you'll see the exact same thing happens here for bromine. So I start off with my bromide ion. It loses an electron and it's forming bromine. But because it's diatomic, I have to add a 2 there, there, and there. So again, I'm showing that I'm starting with an ion and I'm turning it into its elemental form. In this case, these are molecules, whereas over here I had individual atoms. This last one here is tricky, okay? Typically, they don't ask you for this right out, although it's been included in the mark schemes of some 6 markers. If it's H2O, your positive ion is H+, your negative ion is OH-. And OH- is the only example we've got with 2 elements here on the left. The oxygen ends up as O2. The hydrogen ends up part of H2O, and this is essentially how you write the overall equation. I wouldn't worry too much about that particular equation, but that's showing how OH- can be turned into H2O and O2. So the process, all right, 2 parts. You initially split the compound into ions, but then you have to turn those ions back to atoms, or down here back to molecules. If you don't do the step 2, you're not going to get the marks. Okay, step 1 is separating, but the step 2 is the oxidation and the reduction. Sorry, oxidation there is losing electrons. That's where you're going to get your marks. That's how you explain this process. Now there's another little bit to it. So when you're doing electrolysis, you need to consider how you actually made your electrolyte conduct electricity. Did you melt it or did you dissolve it in water? Because unfortunately there's a difference. Molten is pretty straightforward. If you have melted your electrolyte, so let's say I have my NaCl, it's my ionic compound, it's solid, it can't conduct electricity, so I melt it so that the ions are mobile, and now I've got something that I can split using electricity. NaCl liquid contains 2 things. It contains a positive sodium ion and it contains a negative chloride ion. That's all it contains. So when I do this experiment, the positive sodium ion would go to the cathode. It would gain an electron at the cathode and it would become Na. My chloride ion would go to the anode. I would lose an electron and I would end up forming Cl2 molecule, and that's all that would happen. And that's what I've showed here, but just using 2 other examples. KBr as a liquid, PbCl2, so lead chloride as a liquid. The positive ions, which is always the first one, goes to the cathode. They gain the electrons, they become solid atoms. And then on the anode side, I've got my halogens, both turning into diatomic molecules. You're getting oxidation at the anode. So that one is relatively straightforward. Key here, does not contain any hydrogen, so you shouldn't have hydrogen in your answers. But instead of melting your ionic compound, because remember, ionic compounds, very high melting point due to those strong electrostatic forces of attraction. So if I don't melt, if I decide I'm going to chuck it in water and dissolve it instead, cheaper option. However, you do complicate things because you're dissolving it in water, as well as having the Na+ and the Cl- ions that you had from your sodium chloride. The water is going to introduce H+ ions and OH- ions. So instead of just having 1 positive and 1 negative, you've now got 2. So I've shown that down here. NaCl, when it's aqueous, all right, look at the difference in state symbols. That's your clue. When it's liquid, no H2O. When it's aqueous, there is H2O. When it's aqueous, as well as having the sodium and chloride ions, I've now got H+ and OH-. This one here is also aqueous. I've got the copper and the sulfate from my copper sulfate, but I've also got H+ and OH-. So 2 positives and 2 negatives. Although you're getting 2 sets of ions at each electrode, only 1 product is going to form and you need to be able to tell which one. So we're going to start at the cathode. So if I use that same example, At the cathode for NaCl, I had 2 ions going there, my 2 positive ions, sodium and hydrogen. Rule is the least reactive will form, and for that you'll need to use your reactivity series. Using that reactivity series, you'll see that hydrogen is less reactive than sodium, and that means hydrogen is going to form. Once we know it's hydrogen, you need to show that it is being reduced, which is gaining electrons. You need to be able to write that equation for me just like we did on the other side. So hydrogen is positive because it lost an electron. Give it an electron back and it won't be positive anymore. But remember, hydrogen is diatomic. I need a 2, a 2 and a 2. So that's the process that occurs at the cathode. On the other hand, down here, I've got copper sulfate. Okay, the 2 positive ions here are copper and hydrogen. In this example, copper is less reactive than hydrogen. Because it's less reactive, copper is the one that's going to be reduced. So you write an equation for copper. 2 plus charge, because it lost 2 electrons, give it the electrons back. Now it's going to be copper again. So anytime it's aqueous, you will have a metal and you will have hydrogen. Whichever is less reactive is the one you write the reduction equation for. In most cases, it's going to be hydrogen. It's less reactive than most of your metals, but copper is less reactive, and that's going to be your exception. If you had copper or silver, they're the ones that are going to form. At the anode, you've also got 2 ions. So you've got your negative chloride and your negative OH minus. Rule here is simple. If you've got a halogen, the halogen will form. Halogens are group 7s, chlorine is in group 7, so chlorine is going to form. So when I'm writing my half equation, if I'm showing what's being oxidized, I'm going to take Cl minus. It's negative because it gained. If I take electrons away, it won't be negative anymore. You need to remember it's diatomic, 2, 2, 2. The bottom example, I don't have a halogen. All right, I've got sulfur and oxygen. Neither of them are in group 7. So in this case, I've got my sulfate ion and I've got my OH minus ion. And choosing between these two, it's going to be the OH minus ion that gets oxidized. So I have here the OH minus ion gets discharged. I'm removing the charge from OH minus by oxidizing it. That's where I'm getting that language from. Again, this question is not one you typically need to worry about, but that's what would be happening at the anode. In terms of observations, in terms of what you would see, okay, up here, you're making hydrogen. Hydrogen's a gas. You're going to see bubbles. Down here, you're making copper. Copper is a solid, so you would see solid copper, brown copper building up on the cathode. Down here you're going to form chlorine. Chlorine is a gas, you'll see bubbles. Here you're forming water, but you're also forming oxygen. Oxygen's a gas, you're going to see bubbles. Last little bit, there's a core practical where we take copper sulfate, which is what I've got here, and we split it up, and it's always aqueous copper sulfate, always. But we do it in 2 ways. We use it using graphite electrodes and using copper electrodes. So graphite electrodes is just what we've been doing so far. Graphite is inert, it doesn't react, so electrolysis just proceeds as you would expect it to. So I'm saying copper sulfate aqueous is my electrolyte, okay, because it's copper sulfate aqueous. You've got 4 ions present. You've got your copper ions, you've got your sulfate ions, but from the water, you've also got H plus and OH minus. Step 1 is split those ions up. So the 2 positive ions are going to go to the cathode. So I've drawn them here. My 2 negative ions are going to go to the anode. Once you split them up, you've got a choice to make. At the cathode, the least reactive forms. Copper is less reactive than hydrogen, so copper is going to be reduced. It gains the electrons, it forms solid copper, and what you will see is a brown solid building up on that cathode. On this side, your rule is the halogen will form. You don't have a halogen, therefore it has to be OH minus. This is the equation showing OH minus being oxidized, and because you're forming O2 gas, you are going to see bubbles. Copper sulfate is blue, and it's blue because of the copper ions. Over the course of this reaction, those copper ions are being turned into copper atoms. And because of that, the blue color is going to fade as the reaction progresses. You're taking the copper ions, which cause the blue, turning them into copper atoms, which are not blue, they're this brown metal, so that blue color is going to fade. Your other option, the same experiment, but instead of using graphite, I'm actually going to do something different. I'm going to use copper as my electrode. Just a reminder, the electrodes are just these things, the things that I actually connect to the battery and put into the electrolyte. So the electrolyte is still going to be the same. It's still going to be aqueous copper sulfate, but this time I'm using copper. Now the difference here is we said we have to use inert electrodes, things that won't react. this case, copper is going to get involved with this reaction. And we do this in order to purify copper. And what we do is we take impure copper and we put it at the anode, and we take pure copper and we put it at the cathode. I'm going to show you why now in a second, all right? So at the anode, okay, we said copper sulfate is our electrolyte, all right? So copper sulfate aqueous is going to give me Cu2 plus, it's going to give me SO42 minus, it's going to give me OH minus, and it's going to give me H plus. I'm getting these 4 ions from my electrolyte. And if I look what's happening at the anode is positive. The ions that are going to go to the anode are going to be SO42 minus and OH minus. And in this example, that's all I had at the anode, as well as graphite, which doesn't get involved. But now, as well as having these 2 ions at the anode itself is made up from copper, all right, Cu. So now I've got a choice between 3 things. There's going to be one of the ions from my electrolyte that gets oxidized, or is it going to be copper itself? And it's actually copper itself. The electrode is the easiest thing to oxidize. So the copper atoms, which are solid in the electrode, are going to lose 2 electrons to form Cu2 plus ions. And when those ions form, because they are positively charged, they are going to be attracted to the negatively charged cathode, and they're going to migrate to the other side of your beaker. Because all of these copper atoms are being turned into ions and then going to the other side, what you'll see is the anode getting smaller and smaller and smaller. It's going to lose mass. And we said this was impure copper. All of the copper is going to go to the cathode, but the impurities within your electrode, they're just going to fall to the bottom as sludge. When we get over to the cathode, okay, remember at the cathode, I'm going to have my Cu2 plus and my H plus, the 2 positive ions from my electrolyte. I'm also going to get lots of extra Cu2 plus, which are making their way over from the anode. And again, remember, we also have copper at the cathode too. So I've got a choice here between 3. I've got copper, I've got the copper ions that have moved over and the ones from the electrolyte, and then I've also got the H plus from the water. I've got these positive ions, and then I've got the copper that's at the electrode itself. And something has to be reduced, something has to gain electrons. Now out of these 3 things, the thing that finds it easiest to gain electrons is the Cu2 plus. So this is the same as what we saw with graphite. The Cu2 plus ions are going to gain electrons, and you're going to form more solid. So what's going to happen here is you're going to see this brown solid copper is going to build up on the copper electrode, and you're going to end up at the end with more copper. All right, so we're using this to purify copper by putting the pure copper at the cathode and then attracting all of the copper atoms from the anode. At the end, you end up with a bigger piece of pure copper, which we can use for things like wires and pipes. So it's always the pure copper that goes at the cathode. Just remember, the cathode gets bigger, and at the end of the experiment, I want more of the pure copper than the impure copper. So I want the pure copper to get bigger. I'm putting the pure copper at the cathode. So this side, as I said, you are going to see the anode get smaller, it loses mass, and then on this side you're going to see the cathode getting bigger as all the copper ions come over here and join the pure copper electrode. We said before that the CuSO4 solution is blue because of the Cu2 plus ions, and over here what we were doing is we were turning Cu2 plus into solid copper, so that blue color was fading. Over here we're still doing that, we're turning Cu2 plus into solid copper, but we're also making Cu2 plus. And what happens is every copper ion that we make at the anode, we then use up at the cathode. But because the numbers are equal, yes, we're using them up, but we're also making them. That blue color does not fade, and it stays the same throughout. The other thing to know about this practical is in order for that pure copper to be able to stick on to your cathode, you want your cathode to be clean. So often they use like emery boards and they kind of file and smoothen the pure copper so it's nice and smooth and easy for the new copper to stick to. And you can wash it with some water to remove kind of any impurities or any kind of dirt. You can also use propanone. It's an organic solvent to remove any grease or any impurities, but you want those electrodes to be clean. Final thing to say, just thinking of previous exam questions, they did ask an exam question before how you could speed up this process. If you want to speed up this process, you're coming back here to your battery. If you crank up the voltage on your battery, you are going to speed up the rate of the electrolysis. So that's how you would speed things up. Just crank up the voltage on your battery.